So let's think of mapping a building. So our challenge, we have a building, we have no knowledge, prior knowledge of the way the walls are, how many rooms, and so on and so forth, and we want to map it. Obviously, you can think of a 3D map as you can see behind me, or as you can think or imagine a kind of photogrammetry as you start in the first assignment, kind of a 3D point cloud. But for simplicity, let's start with a 2D mapping. Consider a 2D mapping to be a single floor layout of a building where walls are defined in black ink, say, and an area, a room I can room in would be white. So consider the case of a vacuum cleaner. At the first time, it has no prior knowledge of your flat, of your room, of your building. You just got it. It was manufactured in China. You put it maybe on the second floor, and it starts. So at the first time, it may want to have some sort of a mapping of its environment, and a special point of interest in this map would be its charging point. Whenever the task of vacuuming the room is done, or whenever the robotic vacuum cleaner, its battery is going below, say, 50%, it needs to plan its way back, and then have some sort of control algorithm to go all the way back, and then hook to the charging point. The process of mapping while performing localization, known as SLAM, is a simultaneous localization and mapping, is complicated. It's not simple in any manner, although those vacuum cleaners are doing it rather good, and they get better because the first time maybe they have no knowledge of your room, and afterwards, or your building, and afterwards they have a good knowledge of the mapping, and maybe it's better to start with the kids' room and then go to the grown-ups and so on. But this notion is complicated. It involves a lot of algorithms and a lot of kind of in detail engineering and programming details. And in this chapter, we're going to use this challenge to somehow integrate the fields, the material you learn from sensors, control algorithms, state machine, in order to combine them all into a operating SLAM algorithm, not necessarily just for vacuum cleaner, but also for drones or ground robots. Let's talk practice. Consider there is some sort of a building, a 2D map of a building. In this case, let's think of there is a starting point at your main entrance to the building, and we're gonna consider the task of 2D mapping. So I have a building, and maybe there's a starting point, there is a corridor, and to the left there is a room, and then going rightwards a little bit forward along the corridor, there's a strange roundish kind of room, and then going all the way there is a big strange rectangular room with few obstacles in it. Now, consider the case of an autonomous drone or a vacuum cleaner that starts at the start point. We only need to define a starting point, an X and Y, and an angular kind of a compass orientation. Our robot starts in the starting point and start going east. Right, so it has few sensors. For simplicity, as in the drone, let's consider it has a point ranging forward, leftwards, rightwards, backwards. We're in 2D, there's no point of thinking up and down. In our drone, we think that the maximum range of the front or the left, right, backwards rangers is 3 meters. And the sampling rate is 10 hertz per sensor. Its left sensor, range sensor, will in a way go to a point where it bounds not on a corridor, but there's a big jump going all the way to the north wall of room number 1. In this case, we have some sort of discontinuity in the ranging. So we consider the vacuum cleaner keep on going along the corridor, and then its right sensor is sensing this roundish room, and all that time, the front sensor and the back sensors are in a way returning endless, or kind of -1, or just maximum range, because its distance is more than 3 meters. So you may think that in order to have a better map, maybe the vacuum cleaner or the drone, whatever we think of as our autonomous robot, might need to do some sort of yaw maneuvers, so we have a better sampling of the entire region. Just as a snail is moving its tentacles, there's actually more than 2 in many snails, to have some sort of a sensing of the region, our robot might want to do some sort of maneuvers, both in the orientation and its position, in order to have a better mapping. While mapping, one of its main challenges will be to be able to return to home, or more generally thinking about it, to recognize points where it's already been there. So going back will be, oh, I remember that room, I need to continue along the corridor, now I need to take a left, right, and so on and so forth. This process of mapping and localization, as mentioned before, is known as SLAM. And some of our challenges will be to define kind of a SLAM algorithms to cases where the mapping are not perfect. Obviously, you may think of the challenge or the task of returning to home is, in a way, reverse your entire set of actions. And then, so you do perform a U-turn, and then left is right, and you do whatever you do. But consider a bio-inspired algorithm. So you consider a bat. So maybe a bat has its cave or its home, and then it goes from one tree to another tree to a third tree, and so on and so forth. And in the end, it doesn't want to go all the way back along the trees it already visit. It want to take the shortcut and go back home. Going from start to end might be a different path than going end to start. Going back home, in a way, encapsulates the main challenge. But in more formalistic manner, we can think of sub-challenges, such as recognize or classify an intersection where it's an interesting point. I went along the corridor, but I recall that there's a room to the left, or a room to the north, more precisely. And another observation here, which is once I go back, I want to be able to perform a loop closure. A loop closure is a process that intuitively is recognize that I've been here. Not necessarily in the same location, but the view as I see it now is actually the point where I've been along the way at the beginning of my journey, and I just see it from a different angle. The loop closure algorithm or process is actually a key feature in any SLAM algorithm.